Flutube. Get it straight.
Okay, let's look at another Reynolds transport theorem problem again for the conservation of mass. Here we've got a pipe network or in and out fork of a pipe. We've got a velocity coming in at 1. We've got it coming out at 2 here. Let's get my 2, sorry, 2 here, and this is 3 over here. A little hard to read. Coming in at 1, something at 2, going out at 3. We don't really know exactly what it's doing at 2, but let's assume it's going out like I've drawn it here with this arrow. So we're actually trying to find what happens at V2. We've got a leak just to make things interesting at 0.4. That leak is at 0.1 cubic meters per second. So let's look at the transport theorem here. Here it is in its complete form. We know that the material derivative or total derivative in this mass of the system is going to be 0 for steady flow. Let's get rid of this term. Now, this second term, control volume term in this case, is actually going to be 0 as well, because we're going to say it's an incompressible gas, so rho is equal to constant. I'm also going to say it's rigid control volume, so the volume is not going to change at all either. So we end up with two constants, both the density and the volume. So that ends up giving us a 0 here. So the only thing happening really is things are coming in and going out over the control surface. This is a special case called conservation of mass, conservation of flow. Flow in equals flow out. Anything comes in, something has to go out to balance it. So if we have discrete inlets and outlets, and we have uniform flow across those boundaries, then we can just use the velocity times the area. And if we remember that velocities coming in are negative, velocities going out are positive. Flow going out in the case of the leak here, this is a leak 4. And remember that at 2 we've assumed this, but we don't really know for sure. So this is again assuming uniform velocity cross sections. That's why we get this A1 instead of having to integrate there. So we rearrange with the algebra. We get that negative V2 is equal to these terms divided by 0.2. If you do that, you'll get that negative V2 is equal to 4.5, or V2 is equal to negative 4.5. So this negative sign simply tells us that we've drawn the initial assumption of V2 in the wrong direction. A little bit like statics when you ended up with resistance force with a negative number. You guessed in the wrong direction. So that's it for this example.